No, I can't breathe. Hey, I'm waiting for the dumbass to. You in early, Justin.
Technical difficulties. All right, welcome everyone. You guys can hear me okay, right? Oh, and Ethan, remember to record this. Welcome back. All right, welcome everyone. How's everybody's day so far?
Bad.
Of course, your day was bad.
Yours was too.
Hey, no, every day is a good day.
Earlier, bro. No, nothing.
Nikocado avocado. Oh, I finally looked up who that was.
Going.
Yeah, Ethan, you're gonna like share your screen, show everyone who that is.
Put it as my background.
Yeah, put it as your background.
Yeah, that's
Anybody else see that YouTube channel, Nikocado Avocado?
No.
2, 3, 4. Let's give it a few more minutes for people to trickle in.
Yo, Justin.
Mm-hmm.
Hold up, watch this shit.
All right. I'm waiting. What are you watching? That's gonna be your background the whole time. Keep in mind this is being recorded.
No, I got it on. I got it on.
This is definitely going on the compilation, the blooper reel or whatever. All right, let's see. 33. Give it another minute. I forget to ask this the past few.
Shut up.
That's fine. I haven't started yet. I forgot to ask this the past couple of classes, but if you can, if it's possible, turn on your cameras just so I can see faces. It'll all help in the whole atmosphere. You just turned it on for algebra, Yunhan.
Is in a bad mood right now.
I think Aaron's here.
Nah, he said he wasn't gonna be. Probably beating his dick or something.
All right, let's see. 2, 1, 5. All right, so it's 8:33. I guess we'll get started today. How's everyone doing? Doing good? Oh, now I know how the teachers felt during distance learning. All right, so let me see. Let me make sure no one's waiting outside. So last class was pretty bad. There was a lot of new stuff that we learned last class. Kevin, how did you feel about last class?
I wanted to kill myself.
Yeah, exactly. So this class, fortunately, is not going to be as bad as last class. It's not going to be so much new information because a lot of this you guys might have seen before in bio, but there is a lot of information today. So if at any point, we're going to go step by step, if at any point you need me to repeat something or you missed something, please do not hesitate to unmute and ask me to stop and say it again. Likewise, if you ever feel that you are in deep troubling emotional distress and need extreme mental health support, please feel free to reach out to Gautam, the other instructor.
Yeah, Gon was very good with that stuff.
He's maybe better with the emotions. And I think I made somebody cry by accident once. It was, it was in college when we took a general chemistry final. And she told me she called me on the phone and she said she got a 60. And I was like, I scoffed a little bit. Who knew she hung up and cried for 20 minutes. So I don't want a repeat of that episode. So Kevin is okay. So I'm going to start by reviewing last class. Let's see. We got a smaller class today, so let me change the settings. Give me 1 second. Pin my screen so you guys can all see.
Not focused, bro.
Let's see. Let me see if I can focus it. This is the start of every class, focus on this thing. And ready to focus it?
Retarded.
Big black. Oh. My genuine just like.
It takes a while to focus. Sorry. It's the start of it.
Kevin racist? No, it's coming to start searching up computer.
Oh, there it is. How'd you fix it?
Bro, it was dirty.
Okay, thank you.
It might still be dirty.
It usually gets better over time. All right, so you guys can see it okay?
Yeah, put that ad in my head.
We can see it all right? It'll get clearer over time. Thank you, Ethan. All right, so this is a problem we had on the homework. Oh, wow, there it goes. All right, this is a problem we had on the homework. Crystal clear. All right. Did we have any questions before I go over it? Hello, welcome. All right, so this is the homework problem we did last time, and I just want to go over it real quick because today we're going to do more ice boxes. So we start with the question. We have this breaking into this, and we're given K. And we start with 0.5 molar, of CoCl2, and we want to find the amount of CO at equilibrium. So first, we always start by writing our K equation. Remember, K is equal to products over reactants, so we get K is equal to CO and Cl2 divided by CoCl2. And the whole thing equals 6.6 times 10 to the negative 8. All right, so now we're going to do the next step, which is to set up our rice box. Remember, we start with the reaction, and then we start with the initial. We're given that we have 0.5 molar at the beginning, and we have 0 of everything else. Now the change column, since all the coefficients are 1, we're going to subtract x from this side, and then add x to both sides. Add x to both things on this side. So at the end, we get x, and 0.5 minus x. Now we take this column, the equilibrium column, and we're going to plug that into our K equation. Plug it up in there. So now we get K is equal to x times x over 0.5 minus x. And the whole thing equals 6.6 times 10 to the minus 8. And now this turns to x squared because I combine the two x's equals 0.5 minus x equals 6.6 times 10 to the negative 8. So it looks like I have to solve a quadratic, but I'm going to use the approximation trick that I gave you guys last time and just get rid of that x. So now what I do is I take my calculator And I'm going to move the 0.5 to the other side. I'm going to square root it. And I get x is equal to 1.82 times 10 to the negative fourth. And if we look at this column, CO at equilibrium, CO just equals x. Oh man, was I off the camera the whole time? CO equals x. So CO at equilibrium is equal 1.82 times 10 to the negative 4 molar. Any questions on that? We're going to do some more of that today. Oh, look how clear this camera is. Nice. All right. What's that? We had a question? All right. Let's see, let's turn on our cameras if we can, just so I can see you guys. Just so it helps me just get a temperature of the class as they go on. So see if I look out and see everybody's totally lost. Hey, you want to know what's on the other side of this? Does that look familiar? Oh. What's that?
Is that my copy or that different?
That's just scrap paper. All right, so today's class, we're going to talk about acids and bases. So a lot of you guys have taken bio. Who took AP bio? Raised hands? All right, good. Always feel free to just, always feel free to unmute and yell out. So, in bio, we talked about, you guys might have talked about acids and bases. Today, you might see some similarities, even though we cover a lot of material. You might have seen it before. But today, we're going to talk about what acids and bases mean in chemistry. Because in bio, we just talked about them as too acidic or too basic, but we didn't really know what it means. So today, we actually get to learn. So I want to start by drawing out this general reaction. HA plus H2O goes to H3O plus A minus. So this is going to be a little different than the reaction we did a couple of weeks ago. Remember when we did the double displacement reaction? The South Windsor High School English department? So this is a little different when working with acids and bases. If we look closely at the reaction, this left side is the starting materials. This right side is the products. If we focus on this H right here that I'm circling, do you see how this H gets moved? So if we're just looking at the starting material, this H gets mushed onto the H2O, and then it forms H3O. And then we have this leftover A left over. Do we all see how that happens? We just move this H. That's how we know this is an acid-base reaction. The H gets moved. So now let's look at all of these things. I'm going to name all of the things in this reaction. And if we pull out our worksheet for today, we're going to start filling in these basic definitions. This thing right here, this is called the Bronsted acid. All right. And this is something that loses the H. Something that loses H. Can you see how we're pulling it off and putting onto this? This thing up here is called the Bronsted base. And it's something that gains an H. So we took this thing, we stuck an H onto it, that makes it a base because it gets an H added after the reaction. Now, here's where it gets tricky. Everybody good with me so far? We look on the right-hand side. This is called the conjugate acid, which I will abbreviate as Ca. This is tricky. The definition of the conjugate acid is the base after it gains the H. So you see how on this side, it didn't have the H yet, but now it got the H? That makes it a conjugate acid. Likewise, if we look at this thing here, This is called the conjugate base, and I'll abbreviate that as CB. That is the acid after it loses H, after it loses the H. All right? So, yeah?
There's little kids being not nice in the chat.
They always do that. I didn't even look at the chat. So let's look on this side. You notice how on this side there's an acid and a base? And on this side there's also an acid and a base? So on the left and right side, there has to be an acid and a base on each side. All right? So acid and base is really just relative to each other, really just relative to both sides. Here we start with something that has an H, we move it over, and then after that, the thing that lost the H became the conjugate base, and the thing that gained the H became the conjugate acid. Anybody have a question? Any questions about that? My analogy is kind of like we're playing hot potato. Anybody ever play hot potato? You get a big like hot potato, and then you toss it back and forth, and you set a timer. And whoever has the potato at any given time is the it. They're the one who's it. So the H here is kind of like the potato. H is the hydrogen. So the hydrogen just keeps getting tossed back and forth between this thing. And whoever has the hydrogen at any given moment is the acid. So H, the hydrogen, is a potato. Potato. Whoever has H, whoever has the H that we're looking at is the acid. And whoever doesn't have it is the base. So I'm going to give you guys an example. This is the third example on your sheet, at the bottom of your sheet. So we have to identify the conjugate acid, conjugate base, the Bronsted acid, and the Bronsted base. So when we're given these problems and we have to identify all four of these, the key trick is to always start by looking for the H that gets moved. Look for the hydrogen that gets moved. So if we look at this side, this is what it looks like when we start, and then this is what it looks like when we end. Do we all agree that the only difference we see is we took this H here, and we moved it onto here. We stuck it onto the water and turned it to H3O. Therefore, this is automatically the acid. And this, because it had the H to start with, and it lost it. And this here is the base, because it gained the H. If we look on the other side, this used to be the acid, but it lost the H. So now this is the conjugate base. And then now here, this used to be water. That used to be the base, but it gains the H, so now it becomes a conjugate acid. Any questions on that? This was problem 3 at the bottom of your sheet. So the first step, the key step, is to always look at the H that's moving. Let's do problem 4. All right, now, I start by looking at this again. This is what we start with. This is what we end with. Now we have to see which H is getting moved. So it looks like it's this H, one of the hydrogens from water. It gets moved onto this. So once I see what's moving, now I can start to name everything. So somebody unmute and tell me, what is this? What is the name for this thing?
Acid.
Acid, yes, correct. That is the acid. Now, what's this thing then?
Base.
That's the base, correct, because it gains the H after the reaction. Now we look at the other side. So the potato got passed. We passed the potato. Now, what is what on this side?
The first one is the conjugate acid.
Conjugate acid, yeah, because it gains the H. And then what about this? So this used to be water, but then it lost its H. It lost the hydrogen. So here's how we can problem solve. If you're ever sitting on the test and you don't know, always remember that every side of an acid-base reaction has to have an acid and has to have a base. So if we know that this thing is the conjugate acid, we need an acid and a base on each side of the equation. So therefore, this is automatically the conjugate base. We don't even have to think. If we can identify one, we can guess the other one by default because there's only two options. Any questions? So notice here that water, in example 3 and 4, water can be both an acid and a base. It depends on what it's reacting with. And that's what makes water such an important molecule in the body. And that's why our blood is 55% water, because it's perfectly neutral. It can be both an acid and a base. For completion's sake, let me do the first and second example. All right, so I'll do the first one, and then you guys can do the second one. So I have to label everything. That's the first example up here. I look at the hydrogen. Which hydrogen is moving? It looks like this one's moving over here. Therefore, this is the acid, and this is the base, because the acid lost the hydrogen and the base picked it up. Therefore, on this side now, this is the conjugate acid, and this is the conjugate base. All right, so let me have you guys do number 2, just so we're all on the same page. Let's take a look at this. Step 1, which hydrogen is moving?
The one with the HB.
One with HB, yep, all right. And it looks like it's moving over here, right? So what is our acid?
The HB.
HB, yep. Which makes this automatically the base, because we need one of each on each side. Now what about this side?
The H2O, the water is the acid, and then the B is the
Yep.
base.
Conjugate acid, and this is the conjugate base. Perfect. Any questions at all? Excellent. Great job, Abhinav. Did we learn this in biology, that acid and base just has to deal with who has the hydrogen?
Not really.
Or did they just say, oh, okay, just know that acid and base means this?
Yeah.
All right, so let's go a little further. So we know about acid and base, but scientists don't like to say, okay, this is acid, this is base. They have to find a way to quantify how much acid or base they have. So to do that, we have pH. So we flip the page. We're going to talk about pH and POH. Right up here. So now, I'm going to give you guys some life advice. Next year, if Miss Powell, or any teacher, but especially Miss Powell, if Miss Powell asks you what pH stands for, please do not say Pornhub. Do not say porn. Okay, you see, I said it once in college, and the Russian guy sitting next to me got extremely offended. So, I want to avoid that situation. Do not say it stands for Pornhub. Even though the logo kind of... You like that? Kevin made that, the nice logo we have. Thank you, Kevin.
It was some guy already made it before and just plugged in the values.
Oh, really? Nice.
There's some HTML shit.
And I hope everybody got the joke that I put next to it. Get a potential hydrogen, pH, and then you have a search browser history with nothing in it. So I hope we got really just something we've had before. I'm not endorsing pH, by the way. I've never been on, but I'm sure somebody here has. 97% of men, statistics-wise, and 75% of women. All right, so in bio, we learned that pH stands for potential hydrogen, right? I'll write it up here, potential of hydrogen. In chemistry, it's a little different, but it's a similar idea. It both talks about the same thing. It's just that in bio, they kind of simplify things. So, pH and POH, they both refer to the concentrations of H plus, and OH in a solution at equilibrium. Keyword there, at equilibrium. So, I'm going to break it down here. pH is how much H plus, there is in the solution. And H plus is just the hydrogen ion. All right. So we can copy this down in the blanks. POH is how much OH there is in solution. And OH, this is called a hydroxide ion. You don't need to know that. We just call it OH. Now, we're going to talk about the formulas on how this is calculated. And this is where things start to break down. Because we're going to have to talk about this log shit. Everybody took Algebra 2 here. Who actually likes logarithms? Somebody raise their hand. Oh, we got a math guy in here. I can hear the moans. Oh, no, not this again. That was me when I learned this. But as time went on, I started to appreciate logarithms. Now, pH. Here comes the chemistry definition. By definition, is equal to minus log of the concentration of hydrogen. Which means if you know the concentration of hydrogen at equilibrium, you literally just take your calculator, you hit the minus button, down here, you hit the log button, and then you type in the number, whatever the hydrogen concentration is, and you just push equal. That's how simple it is. Now, something I should also mention is the concentration of H plus is always equal to the concentration of H3O. So you can use either one when you're solving for pH. So you could also say pH equals minus log H3O. It's the same thing. All right? So that's what P means. The letter P, it literally just means minus log. And I know in biology they try to simplify it to tell you pH stands for potential of hydrogen. In chemistry, P just means minus log. So therefore, POH is equal to minus log times the OH concentration. All right, and I put it all in a nice little nifty box for you guys, all the formulas you're going to need. Now the next formula, this is the one that people ask, well, where does that come from? pH plus POH equals 14. Did we learn that in bio? Yes, no? Nobody? Oh, we didn't learn that in bio? Uh-oh. All right, so this is just a mathematical fact. If you want to know where this comes from, because people say, where does 14 come from? It's just a random number. If you want to know where it comes from, ask me after class, and I can prove it for you. I'll derive the whole thing. It's a simple mathematic calculation using logarithmic properties. But I don't want to confuse you guys and eat up too much of your time if you don't want to know. So for the purposes of this class and for AP Chemistry, please accept that pH plus POH equals 14. So if we know the pH and we want to find the POH, we just need to subtract it from 14. All right? Any questions? Oh, Kevin's about to lose his mind. All right, so let me do the first problem that we have on this sheet. All right, so a solution has an H concentration of 0.0039 molar. Find the pH. I'm going to show you guys how simple this is. We literally start with pH equals minus log hydrogen, and we just plug it in. And we whip out the calculator, minus log 0.0039, and we get the pH equals 2.4. Now, in AP Chemistry, you'll have a calculator when you do this. If anyone here wants to become a doctor, when you take the medical school entrance exam, they won't give you a calculator for this. So you have to do logs in your head. But for now, we can use a calculator. Let's do an example. A solution has an OH concentration of 0.052. Find pOH. All right. Let me just center the page. This one, watch this. This is pretty cool. We're going to start with pOH equals minus log OH. And we plug this shit in, just like before. So we put it into our calculator. Minus log 0.052 equals pOH equals 1.28. Everybody got that? Not as bad as last class, right? All right, so next is a solution has OH of 2.5 times 10 to the minus 6. Find pH. Oh, shit. So we're in trouble now because we have OH and we want to find pH. But here's what you do. If we can find the amount of pOH by using the formula, we can find what pH is after that. So the first thing we do is whenever you have OH, you will always be working with pOH. So we take this, we're going to plug it into here to find pOH. And when we plug it into our calculator, I have it done here, we get pOH is equal to 5.6. But the question asks for pH. So now we have to use pH plus pOH equals 14. We know that pOH is 5.6. So we just have to do 14 minus 5.6, and that gives us the pH is equal to 8.4. Any questions on that? So you literally plug it in. So far, so good, right? Am I going too fast, too slow? Someone want to give me a quick temperature check? All right, so it's a good pace is what I'm getting at. All right, now, here's the thing though. Let's say I have a problem like this. Let's say the problem gives me, and this isn't on your sheet, but you can copy it down. Let's say the pH is equal to 2.4. So how do I find, what if I want to find the concentration H? So in this case, we're going backwards. We know the pH, but we want to find how much H is in the solution. So to do that, first we have to use some mathematics. And I'm going to prove how to do it. So of course, to do that, we have to review our log rules. Oh boy, nobody likes logs. But hang on for 1 second. I'm going to give you guys a detour. So who had Devasy for Algebra 2 here? Mrs. Devasy? Oh boy, I feel bad for you. Nah, I'm just kidding. She's a really good teacher for AP Calc, but oh my god, her Algebra 2 class was so bad. But I'm going to review logs for you guys. So on the very first thing on your next page, it has a brief review of logarithms. Log base, so when we have log base 10 of x equals y, this is a 10 right here. There's a mathematical law that says we can rewrite it in exponential form. And for those of you that had Devasy, she always said the exponent comes after the equal sign. So we can take the base and we can write it as 10 raised to the y is equal to x. Does everybody, does that make sense to everybody? So what we can do now is we can start with pH is equal to minus log base 10 of hydrogen concentration. I'm going to isolate the log, so I'm going to divide both sides by -1. So I get negative pH is equal to log base 10 of H. But this looks a lot like y equals log base 10 of x. Right? This is our y value, and this is our x value. So now, by mathematical law, if we're allowed to say 10, if this turns to 10 raised to the y equals x, I can also take this and I can do 10 raised to the minus ph is equal to h. And that's the formula right there. That's how you derive it. So you can do two things. You can either memorize this, memorize the formula, or you do what I do every time, and I just prove how it's done every time I do one of these problems. So up here, when it says the pH is 2.4, what's the concentration H? Now that we have this formula, we literally just do 10. We raise it to negative 2.4. I put it in my calculator, and I get the concentration is equal to 0.0039 molar. That's the H concentration. Any questions on that? All right. For the next part, I want to talk about something I skipped on the very first page. I skipped this part right here, strong acids and weak acids. So I'm going to talk about what a strong acid is. And again, if you guys are looking for where to write down, it's right on the very first page of the packet. It says strong acid. So here, a strong acid means an acid where every single molecule of the acid loses the H. Which means if we have HCl, every single molecule is going to break up and it's going to lose its H. Therefore, if we have 2 molar of HCl, we know that we have 2 molar of H, of hydrogen ion, because every single molecule of HCl broke up. It split up to release the H. So that's a strong acid. A weak acid is where only some molecules lose H. Which means that, let's say an example of a weak acid is HF, hydrofluoric acid. Let's say I have 2 molar concentration of HF. We don't know how much hydrogen we have because not every single molecule of HF breaks up into ions and loses the H. So we don't know. And now, just a couple of rules that I put on the sheet that we might have to know. I know this is a boring class, kind of like last class. All right. If the starting acid is strong, this is the first rule we have on that sheet, then the conjugate base is extremely weak. Which means it does nothing in the solution. The conjugate base does nothing in the solution. On the flip side, if the starting acid is weak, then the conjugate base is decent. It does affect the solution. So I'll put it here, affects solution, whereas up here, does nothing. It just sits and floats and chills around. It's the couch potato.
Like, wow.
Kind of like that picture on Kevin's background. You see? Everybody look at Kevin's background right there. Right there. That's the definition of a weak conjugate base. It's extremely weak. It does nothing. It just sits and it does nothing at all. It does not react. And how do you know if the conjugate base is weak? If the starting acid is strong. Any questions? On On the worksheet, on the packet, I was gonna explain why the rules are true, but that's if you want to know why, see me after class. It's not always necessary to know why. I can talk about it after class if you want. All right. Any questions? I know it's a lot of information today, but we've seen some of this from bio, or well, maybe not as I thought. Now let's talk about how to do the math with strong acid and base. All right, I'm looking at this page right here. All right, here we go. So if the acid is strong, then we assume that the amount of hydrogen equals the amount of starting material. Which means that if we have 3 molar HBr is a strong acid, then we automatically know that the amount of H is equal to 3 molar. We just take the same number. They're equal. Likewise, if we have a strong base, then we assume that the OH is equal to the starting base. So let's say I have LiOH. LiOH is a strong base. If we have 2 molar LiOH, then we automatically know that OH is equal to 2 molar. Are we good? So how do you do math with this? It's the same as we did before. If a solution is 2.5 molar HBr, what is the pH? So we have the starting material, the starting amount. We start with 2.5 times 10 to the minus 9 molar HBr. So we automatically know that the amount of H is equal to 2.9 times 10 to the minus 9 molar. So now we just plug this into our formula for pH. And when we put in the calculator, we get pH equals 8.6. Any questions? Let's look at the next problem. The very last problem down here. You have a solution and the concentration of NaOH is 6 times 3 times 10 to the minus 5. Find the pH. Do you guys want to try this first before I go over it? As a hint, you have to find pOH first. So we know that if we start with this much NaOH, since it's a strong base, we automatically know the amount of OH is equal to 6.3 times 10 to the minus 5. So we simply just plug in to find pOH. And when I put it in the calculator, we get the pOH is equal to 4.2. Now to find pH, we just do pH plus pOH equals 14. So pH is equal to 14 minus 4.2. And pH, our final answer is 9.8. Does that make sense? What do we think? A lot of stuff? And that's kind of a dry topic. Anyone have any questions before I do one last thing? All right, so let's talk about weak acids and bases. So HF stands for holy fuck, what are we doing? So HF is a weak acid. And you're always, in this class and in AP Chem, you guys are going to be told what's strong, what's weak. You only need to know how to identify if you take organic chemistry. Then you have to be able to look at it and tell it's weak. So if we have 1 molar of HF and we want to find the pH, since it's weak, not every single HF breaks up to release the H. So we don't really know what the H concentration is just by looking at it. So what we have to do is if the acid is weak, not all the H is released. So we have to use equilibrium. And we have to use K. Oh my god, we have to do equilibrium again. I can hear the moans coming from the crowds. Who likes equilibrium? Did anybody like last week's lesson? Yeah, nobody likes equilibrium. Alright, so what happens is, to do equilibrium, we have to use K again. So if we remember from last time, K is products over reactants. So this is our general equation when we're dealing with acids. We start with an H acid and it breaks up. When we're doing these problems, we only focus on the acid. We don't forget about the base. So this is only focus on acid. So K is equal to products over reactants. So K is equal to the products H and A over HA. And to specify we're working with acids, we write a little a under the K. So we have Ka is equal to that. Similarly, when we're talking about bases, this is the general formula that we have for bases. And you guys just have to know this formula. There's really no proof as to how it works. We have K is equal to OH times HB over B. And we don't include H2O because it's a liquid. We don't include in the K. So we have KB is equal to that. So we have Ka, which is a ratio when working with acids, and Kb is a ratio when working with bases. And I'm going to show you guys how that all plays out in just a second. Are we good with this? All right. Let me show us how to do the problem. So this is a hard problem, similar to the kinds that they'll make you do in AP Chemistry. We have 0.1 molar of HF, and Ka is equal to that. Find the pH. That's the very first problem up here. The first thing we do, and I wrote the steps on the side in case you guys need it. Step 1 is to write the expression for K. So we have HF, and it's going to break up into H and F. Alternatively, we could also write HA breaking up into H and A. That's just a generic formula. So we could pick either one. So we're going to write our expression for Ka, which is going to be Ka is equal to products over reactants. So we get H times F over HF. Any question on that? The next step is we have to do a rice box. Because since it's a weak acid, it involves some equilibrium. So just like last time, I'm going to start by writing RICE. Our expression, our equation is going to go here. Now we plug in the initial stuff. So we're given that we start with 1 molar. And remember, it has to be in molarity when we plug in. It's already in molarity, so we just plug in 1. And at the start, we have 0H and 0F. But then as the reaction goes on, we're going to subtract 1, since all the coefficients are 1, and we're going to add 1 to the product side. So at the end, we get X times X and 1 minus X. Pause about to end. So now we take this and we plug it into our K equation, the amounts at equilibrium. So we get Ka is equal to X times X over 1 minus X. But we're given that Ka equals this, 6.6 times 10 to the minus 4. So we set the whole equal time to that. Now we have to solve for X. So I get X squared. I'm going to combine these two X. Times 10 to the minus 4. So I have to solve a quadratic. But I'm going to do that approximation I showed you last time. Just get rid of that X. And when I square root both sides, I get X is equal to 0.0257. Anybody have a question on how I got that? But we're not done yet. It asks for X. We want to know the pH. So we look at the equilibrium ice table again, and we see that at equilibrium, hydrogen, the amount of H is equal to X. Therefore, since X is equal to this, and the amount of hydrogen equals X, the amount of hydrogen equals 0.0257. Now that we know the hydrogen at equilibrium, we're going to plug into our formula for pH. pH is equal to minus log H. I'm going to take this and plug it in because that's concentration. And when I put this into a calculator, this is step 3, plugging into the pH formula. I get the pH is equal to 1.59. And that's how you do that kind of problem. Any question? So at the beginning, when they gave me Ka, that immediately told me I had to work with Ka. So when you see Ka at the beginning, you immediately know you're working with this. You're working with acids. I'm going to leave it up here in case anyone wants to copy it down. I hope I can refocus this after. I'll just move it up and down so you guys can see it. All right, I have one last example problem I'm going to show you, and it's the same thing, but just with a base. So now we have a solution, the very last problem on that page, 0.5 molar NH3. Kb, it gives us Kb, which means we're working with a base this time. Kb is equal to that. Find the pH. So always go back to the steps I wrote out, and this is what goes through my head when I take the exams too. This is how I aced general chemistry in college. Step 1 is to write the expression for K. So I have B plus H2O goes to OH plus HB. That's the generic formula for bases that we talked about up here. And what happens is I can either fit our base into this generic formula, this is the base, or I can just leave it as is, but I'm going to fit it in. So NH3 is the base. H2O is going to react with H2O. So when it reacts, I'm going to take one of these H's and I'm going to move it over to water. And that's going to give me NH4 plus OH. Oh, these should be switched. So it would be OH plus NH4. Do you see how I fit the base into the generic formula? So now, step 2. If anyone has a question, feel free to unmute too. Step 2 is to do the rice box. So we're going to start with our reaction up here. NH3. And just so I can prove to you guys that you can use the general formula instead of the specific formula, I'm going to write it like this. So we start with 0.5 molar of NH3. So that's going to go here because NH3 was our base. And then everything else was 0. Oh, and I have to write the the Kb. So Kb is equal to pH OH over B. That's the Kb formula that we got from the very beginning of our lesson. So, are we good? H2O. Notice that H2O is not in our equation for K, so we can just ignore it. So the reaction goes on. Since the coefficients are all 1, I'm going to subtract x here, and I'm going to add x here. So at the end, we get x on the right side and 0.5 minus x. Now we're at equilibrium. I'm going to take these values. I'm going to plug them into K. So I get Kb is equal to x squared, because there's 2 x's, divided by 0.5 minus x. And just so I don't have to solve a quadratic, I'm going to get rid of that x. Kb is equal to 1.8 times 10 to the negative 5th, because it gave me that at the beginning of the problem. And now I just solve for x. And when I do the algebra, I get x equals 0.003. And since OH, according to our equilibrium chart, at equilibrium, OH equals x, that means OH is equal to 0.003. Now that we have OH, we can find POH. POH equals minus log OH. So we're going to plug this up here. pH is equal to minus log 0.003. So I get POH is equal to 2.52. All right? And that was step 3. We plugged everything in. But wait, the question doesn't ask for POH. It asks for pH. So guess what we got to do now? We got to use...
fucking ass. What did you put in the log?
Oh, the log is OH. So we took this number and we plug it in for there. So now we got POH equals 2.52. And to find pH, we just use that simple rule, pH plus POH is equal to 14. And we know POH is 2.52. So when we subtract it from 14 to solve for pH, we get pH equals 11.48. And that's the final answer. All right, that is the last problem. Any questions you guys have? Yeah, you can raise your hand. The meeting might kick me out, but if it does kick me out in the middle of your question, I'm going to send an extension link, so I'm going to come back after that, all right? But go ahead. What's your question?
So when you get rid of the minus x, are you allowed to just do that? Does that x go anywhere?
Yeah, you're actually allowed to just do that, because if we kept the x right here, we would have to solve a quadratic. And we don't want to do that. So what the chemists all over the world have decided, and what AP Chemistry allows you to do, you just get rid of that x. Anytime it looks like you have to solve a quadratic. And the reason being is that x is so small, it shouldn't matter if you get rid of it or not.
Okay, thank you.
All right, so now we go into the worksheet that we have for today. I will stay here in case anyone has remaining questions, but as soon as it kicks me off, I'll send an extension link. You guys are free to work on it on your own or come back in case you need any help. This is a tough lesson. Trust me, acids and bases is known to be the hardest in chemistry.